So this being a physics class, we do a lot of graphing. In this video, we're going to be talking about graphing and the electric potential. So by the end of this video, you'll be able to evaluate graphs involving the electric potential. So one fundamental term here, guys, evaluate. We're going to be talking about all of the different amounts of information you can gather from a graph of electric potential. So let's go ahead and start by creating a potential distance graph for parallel plates. And what I'm going to do is I'm going to go ahead and I'm going to say that I have a potential difference of 10 volts. When I am at the top of my plates, I have a potential difference of 0 volts when I am at the bottom. And I'm going to say that I've got a potential difference of 5 volts directly between them. So, essentially what should happen is as I move from the positive plate to the negative plate, my potential difference will drop depending on how far I've moved. And in fact, it should drop in a linear fashion. So let's go ahead and graph what I just saw. So I'm going to say that my x-axis is the distance from my 0 volt plate. So that's how far I am from that bottom plate where I have zero voltage, zero potential, which I'm going to go ahead and measure in centimeters. And then I'm going to say that my y-axis is going to be my potential, measured in, of course, volts. So as you can remember, my distance from the 0 volt plate, so we're going to say that total distance was 10 centimeters. Nice and easy, right? So I'm going to say each of these blocks is 1 centimeter. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 centimeters. I'm going to say that each of these blocks on my y-axis is 1 volt. And so at when I'm 0 centimeters from my bottom plate, I'm going to have a potential of 0 volts. Once I move a centimeter away, I'll have a potential difference of 1 volt. 2 centimeters, I'll have a potential difference of 2 volts. And when I've gone 10 centimeters away and I've reached my top plate, I will have a potential difference of 10 volts. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 9, 10 volts. And so I'm going to go ahead and connect those in a nice, straight, easy line. Now, this is a nice straight line, so it is going to be very easy for me to figure out the slope of my line. So let me go ahead and do that. I'm going to go ahead and shrink this down a little to give myself some extra space. And I'm going to find the slope of my line. So my slope, m, also known as my gradient, is given by delta v, my change in potential, over my change in distance. Or, as I might actually put it here, is my change in x. And from that slope, that gradient, we can actually find our electric field strength. So remember, our electric field is given by the voltage between two parallel plates divided by how far apart they are from one another. But we also know that we also define our positive plate as our plate with some kind of voltage and our negative plate as our 0 volt plate. So the closer a positive charge gets to the negative plate, the lower its potential is. So what that means is that traveling in the opposite direction, so remember this is my electric field, traveling in the opposite direction of my electric field is going to give my charge more potential. So that is why we're going to introduce this negative sign here. So my electric field is going to equal negative delta V over delta X, or the negative slope of my voltage versus position graph. So let's go ahead and graph electric potential E versus distance in meters or in centimeters. So remember, I found that my the slope of my graph, m, is given by was 1 volt per centimeter or 100 volts per meter. I also know that E is equal to, my electric field is equal to negative M. So my electric field will be negative 100 volts per meter for my entire graph. And again, this is from my very first graph. So I'm going to go ahead, I'm going to say this is negative 100. Here we have our 10 meters. And my graph of electric potential, or of electric field versus distance, is going to be a straight line for the entire distance between my two plates. And this is what we expected, right? The electric field between two parallel plates is constant. However, I'm not quite done yet. So remember, we found that our electric field was equal to negative delta V over delta X, which we could also say means that delta V is equal to negative E times delta X. Or our electric field, or our voltage, our potential, at any point in space, so at 1 centimeter, 2 centimeters, 3 centimeters, etc., is equal to the area under my graph at that point in space. So the area that I'm highlighting right now is my voltage at 1 centimeter. So let's go ahead and test that. So our electric field, so delta V is going to equal my electric field, or the negative of my electric field, so negative 100 times my distance, which is 1 centimeter, or 1 times 10 to the negative 2 meters, which gives me voltage of my voltage of 1. So as you remember from our first graph, that is in fact our voltage at 1 centimeter. And we can continue doing this for all of our other areas. And so from our electric field versus distance graph, we can construct a voltage versus distance graph and vice versa. So think of this as your voltage versus time graph and your acceleration versus time graph. They're going to be very similar for you. So let's go ahead and talk about our takeaways for graphing parallel plates. So first of all, the characteristic shapes of our two graphs. So for our voltage versus distance graph, the characteristic shape is going to be a straight line with a positive slope. For our electric field versus distance graph, our characteristic shape is going to be a flat line with a negative value. Second, we can go from one graph to the other. So I can go from my voltage versus distance graph to my field versus distance graph using my negative slope. And I can go from my electric field versus distance graph to my voltage versus distance graph using the negative of my area. So there you have it, folks. You know your way around graphing parallel plates.